Welcome to Pomodoro Joe for Thursday, June 1st, 2023. Today we're looking at LeetCode problem 1091. Shortest path in binary matrix. This is a medium problem. Given an n by n binary matrix grid, return the length of the shortest clear path in the matrix. If there's no clear path, return -1. A clear path in a binary matrix is a path from the top left cell, i.e. 0, 0, to the bottom right cell, i.e. n-1, n-1, such that all the visited cells in the path are 0. All the adjacent cells in the path are 8-directionally connected, i.e. they are different and they share an edge or a corner. The length of a clear path is the number of visited cells in the path. Okay, and then we have an example here. Start in the upper left, 0, 0. We go down to the bottom right, and there's only one move there, but it looks like we return 2 because it includes 2 cells. One move, but 2 cells. Okay, next path here. We have 1, 2, 3, 4. Yep, looks like we got 4. And then finally, oh, they're being sneaky. So this starts with the first cell at 0, 0 having a 1. So you can't do this one. You have to return -1. All right, so that's a sneaky edge case we'll have to keep an eye on. All right, and with that, we'll put 25 minutes on the Pomodoro timer and get started. So this seems like a pretty straightforward grid traversal, and I'll be using a breadth first search for this. So one thing, anytime you run across a grid traversal, when they ask for the shortest path or the longest path, some type of comparison, you'll most likely want to do a breadth first search, especially with these shortest paths. This is kind of like, you can think of it as you're radiating out from the start point. You have these concentric circles that radiate out. That way you can compare each of these paths and they're about the same length. If you did a depth first search, you'll start with one really long path to get to the end, and just calculating that one path might take up all your time. So in order to compare all the paths, it's best to do a breadth first search when you're looking for the shortest path. Okay. So with that, we will get started. Now I'm going to make a couple, helper variables out here. So one will be my modifiers. So the modifiers will be the modifiers that I use to advance to one of the next cells. So we can go up, down, left, right, but we can also go up, left, up, right, and down, right. So we have to keep track of, looks like, let me scroll down here. So if this is our cell, we've got 3, 6, 7, 8 options. So we need to keep track of 8 different modifiers here. I will make this a list, and let's see, I'm going to put it on multiple lines to make it easier for us to see. So in the first option is, I'm going to take this as our center. We can go up and to the left. So going up and to the left is a -1, and going up is a +1. All right, so that's our first. Then if we just go straight up from where we're at, we don't move any in the x direction, but we move 1 in the y direction. So that's 0, +1. And last, we're going up and to the right, so that will be a +1 and a +1. That's our first row. Now our middle row is a little bit different. We only have this move to the left or this move to the right. There's only 2 options here. So move to the left, we go -1 in the x direction, but 0 in the y direction. I'm actually going to add some more spaces here. And then moving to the right, we will go 1 in the x direction, but again 0 in the y direction. And now our last row here. Let's see. Again, we'll go -1 to the left, and we'll go -1 to go down. I might add some spaces here to keep these lined up. Then in the middle, we'll just go down. So we have 0 and -1. And again, I think I might realign these a little bit. And then the last option is we go down and to the right. So going to the right is 1 and going down is -1. All right, and we can look for some patterns in here. Like this is always going to be moving to the left, so the x will be -1. This will be moving to the right, so the x will be +1. Up here, We're moving up, so the y's will be 1. Down here, we're moving down, so the y's will be -1. Okay, so I think we've covered our bases with our different modifiers. And of course, this one in the middle would be 0, 0, but we don't actually need to do that one because that is actually the cell that we're at. And I will do one more little alignment, just kind of make things a little clean here. All right, so these are our modifiers. What else do we need? Well, we'll need our Q. We'll need to know where we're starting from and where we're going to. So this will keep track of all the different cells that we need to go to next. So our Q, another rule of thumb here, if you're going breadth first search, you'll use a queue. So that will be a first in, first out data structure. If you're doing a depth first search, you'll use a stack. One way you can think of this is if you're thinking alphabetically, breadth first, B, comes before depth first, D, and Q comes before stack. Okay, so what we need to keep track of? Well, we need to know our coordinates, and we're going to start at 0, 0. Oh, but what about our base case, this tricky edge case here? Let's put that up here before I forget it. Okay, so if our grid at 0, 0 is equal to 1, then we have to return -1. And I imagine if they did this for the very first cell, they probably have the same for the very last cell, so let's also check that. Now in Python, I can do -1s here. If you're using a different language, you might have to find the length of the grid first and then put that length as the very last element, or sometimes they have like last as one of your options, so you can do grid.last sort of thing. Let's see if that one, all right, so if our starting point or our ending point is a 1, we can't actually traverse this on a clear path, so we'll return -1. Okay, so we have our Q. So our Q will start off at our starting point 0, 0, but we also need to keep track of how many steps we've taken, how long is this path. So we'll add another element here, 0, or we can start it at 1, I guess, because we know we're starting with one cell in our path. All right, so this will be X, Y, and then our number of steps or number of cells in the path. And one other thing we'll need, generally when you're doing a breadth first or depth first search on a grid traversal, you'll need to keep track of which cells you've already visited so you don't end up visiting them again. So I'll have some visited, and I like using a set for this. Now we could use a grid, we could actually use the grid itself and modify the grid as we go. I don't like doing that because it's generally not a good practice to modify your inputs unless you're explicitly told you can. So in our case, I'm just going to use a set. We could also make a copy of the grid and just put markers in our copy, so that way we don't end up going back to the same cells again. But this is just my preferred way of doing it. And now we get to our breadth first search. So now while we have some Q, we'll pop our X, Y, and step count out of our Q here. So this will be X, Y, and I don't know if I'll call it cell count or steps. I'll call it steps. And that will just be equal to our Q. And now for a breadth first search, we'll pop at 0. So we're going to be taking the first element out of our Q. So this is first in, first out. I'll be popping 0. So this is a breadth first search. If you wanted to do a depth first search, you can pop the last element in our queue, which would be more like popping the top of the stack. That would be a depth first search. But this is breadth first, so we're going to pop 0, pop the left element. Okay, now the real work begins. I guess I do need another piece of information here. I need to know whether or not I've reached the end. So if this X and Y coordinate is equal to our target, then we're at the end. Now, I haven't actually defined target yet, so I'll probably do that up here with our modifiers. All right, but if we have reached the end, then we can just return our steps. Now, in this case, you might think, well, how do we know that this is the shortest path? How do we know we don't need to compare it to other paths? Well, it's the first one that reaches the target. So because we're doing breadth first, all of our levels, I guess, the levels away from our start are sort of aligned together in our queue. So the first one that reaches our target will actually be the shortest path. Okay, so let's define our target before I forget that. So our target, this will be n-1, n-1. It's defined here. Oh, we don't know what n is, so let's get n here. And actually, I'm going to, yeah, let's do that. So n will be the length of our grid. So our target will be n minus 1 at n minus 1. Okay. Now we have our end case where we return the number of steps. Now we need to actually do our, I wouldn't call them recursive cases, I guess, but we can do all our directional cases. And there will be a lot of caveats on here too. All right, so for every modifier in our modifiers, we'll get the new x and y out. So we'll have a next x. That's just going to equal our current x plus our modifier's modified x. And our next y will be similar. That's just going to be our current y plus our modifier's y. So you can see we're going to take our current x and we'll be adding -1 and our current y and adding +1 to go up and to the left. So that's our next x and next y. Now we need to do a bunch of checks to see if we're still in bounds. Once we check if we're in bounds, if we are in bounds, then we need to check whether or not this grid space has a 0 in it or a 1 in it. And if we make it through all of these checks, then we can add this cell, this next xy cell, to our queue so that we can process that cell next. Or maybe not next, but we can process that cell in the future. Okay, so here's all our checks. First, let's do a bounds check. If next x is less than 0, then we can't use this one, so we'll move on. Or I'll say next y is less than 0. Or if the next x is greater than some maximum x. Now I don't have this defined yet, so I will have to define that too. Or next y is greater than max y. So if any of these conditions are true, this cell is out of bounds, we'll just continue. All right, let's go define our max x and max y. That's very much related to this n. So max x is just n minus 1, and max y is n minus 1. Now one thing I could do, because we're doing this n minus 1 4 times, we could actually just do n minus 1 once and use the same variable. I'm not going to do that for now. You understand what this means. It's not going to save us a ton of time just to do this once. So for now, I'm going to make it explicit and we'll just keep these as n minus 1. Okay. Now we've checked to see if we're in bounds. We still need to check two other pieces. We need to check if we've already visited this cell, and we need to check to see if this cell is a 0. So let's see, or maybe I'll say a cell is 1. That lets me exit early. So let's do that. All right. So if the grid at this next x, usually I like to use screen coordinates where I use y first and then x. In this case, because it's square, it doesn't really matter, but I am going to do it anyway. So the grid is next y and next x. If that is equal to a 1, then this is not a clear path, or this cell is not in the clear path, so we won't traverse down this cell. Or if our next x and next y is in our visited, then we've already been to this cell, so we'll just move on. Wow, this is a lot of cases where we're just moving on. Finally, we have a cell that is within our bounds, we haven't visited it yet, and it has a clear path, it's a 0. At this point, we will add this cell to our queue for processing. So, queue.append, and it's going to be not just our next x and next y. We will take the next x and next y, but we also need to take our steps and add 1 to that because this is one more cell in our path. All right, let's see, this is looking pretty good. And that's it. So we will add these cells to our queue. We will keep processing our queue until we reach the end. We could do one thing here where we check the end and early out instead of putting this cell on our queue. That actually might save us a little bit. We'll come back and check that out later. Now the final piece to this one If we make it through this entire while loop and we never reach the end, that means there's no clear path to the end, so we can return -1. All right, I think this is pretty good. Let's give this a shot and see how many typos I made. No typos, we pass. Wow. All right, let's submit this and see how we do. Oh, and we get a time limit exceeded. We only beat 37 out of 89, so that's not great. Okay, so a couple things we can do. One thing is we're using a standard list here instead of a data structure that's actually designed for popping things in and out of the queues. So we're going to change this to a deque. That is a D-E-Q-U-E. That stands for double-ended queue. So this is actually optimized for quick pushing and popping. So we will actually change this to a deque, and then we have to change our pop 0 to a pop left. So that should help us a little bit. Let's see if that does get us past this one test case at least. Still time limit exceeded. All right, so the other thing we could do is down here, we could actually do our exit out early as soon as we reach our endpoint. So we already know that the endpoint is not going to have a 1 in it. So as soon as we reach the endpoint, let's just jump out. So we can move this here. I guess we still need to keep it in here just in case. This might be a little tricky. Let's just put it in here, add an additional 1. So in this case, we do need to return steps +1. All right, see if this saves us anything. Still time limit exceeded. Oh man, might be running out of tricks on this one. Oh, you know what? I totally missed something. Oh, you probably spotted this and you didn't tell me. What am I missing here? It's so obvious. I never put our cell in our visited. So we can actually try it without this and do this the right way. We need to add this cell to our visited. And we're not adding the cell with the step, it's just the X and Y. So we'll do that here. I was wondering why it was taking so long. Okay, that was my oversight. I completely missed that. Yes, if we are in visited, we want to continue, but that means we actually have to put our cell in the visited when we plan on visiting it. So we're going to put it in our visited before we actually visit it. This is just a little bit of a time saver in case we end up going to the same cell multiple times. So from, let's say, this cell over here, this cell up here is within its step range. And this cell also has that cell within its step range. Same with this cell. So we end up having the same cell basically in the same in step range of multiple cells. So as soon as we queue it, so as soon as we put this in the queue, we want to add it to the visited so that any other future cell that might step to that cell will already avoid stepping into that cell that we've added to our queue. All right, so this should make a difference. This should make all the difference. Okay, and we pass. Let's see if this will pass all the runtime checks. And we pass, and we do okay. Not great, but okay. We beat 53% for runtime and 12% for memory, so that's not too bad. All right, let's jump back here really quick. I do kind of want to try that early out just to see if it saves us anything. So let's jump in here and do that. So one thing is, as soon as we get to the end, we can early out. If we don't do this early out, then we end up basically going through a whole bunch of, like, we've queued our end target into our queue, and we have to pop all of these other elements off the queue just to reach the end target that we've already queued up. So this might save us a little bit. But we do have to return steps +1. See if this still works, and then see if that saves us anything. It actually doesn't save us anything. That surprises me. We're at 51% for runtime and 23% for memory. So we do, I guess, a little bit better in memory. We double, yeah, okay. We do a lot better in memory, but we do a little bit worse in our runtime. I'm surprised by that. I thought this would actually save us some runtime. Okay, there are some other things we could be doing here. I'm not going to get into it because they're a little bit more complicated. They involve using heaps. If you are interested, I recommend doing this problem and then checking out other people's solutions, because there's lots of different ways you can do this one and they're really interesting. Okay, well, that is it for me. Our best score on this one was a 53% with 12% for memory. And that's the best I got today. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you remember the trick about depth first versus breadth first. And hope you can go out and write better code.